Welcome back! In part 1 we saw how the measured per bulb variance, when computed from sets of 6 Brighty bulbs, can vary quite a bit. We ultimately created a PDF of those standard deviations and saw how this PDF has the same appearance regardless of the underlying standard deviation. We left off with the thought that there's something mathematically the same between these two curves, something that we can exploit to create a student's t-distribution. With that in mind, let's estimate the probability of being between 10% below and 10% above the underlying standard deviation for each of these. For the low standard deviation case, this means the probability of being between 0.9 and 1.1 watts. We can see that we have a width of 0.2 and an average height of roughly 1.1. Can you predict what I'm going to do with the high standard deviation case? Please, try to reason it out for yourself. It's a bit hard for me to admit this, but you'll learn things best when you pause and try to reason through things for yourself, not when you're passively listening to me. These videos are really intended to jumpstart an inner dialogue that may take you to new, unimagined, and wonderful places. Okay, for the high standard deviation case, 10% below and 10% above means 9 and 11. So that gives us this area here. How do these areas compare? You should see that this area has 10 times the width, or 2, but only 1/10 of the height, or close to 0.11. Also, as mentioned before, they both have the same basic shape. The only differences are this fixed horizontal and vertical stretching. So hopefully, you can see that the areas of these regions are exactly the same. And this is a key point. Regardless of what the underlying standard deviation is, we'll always have that same 24.1% chance that our measured per bulb standard deviation is within a plus or minus 10% region of our underlying per bulb standard deviation. As long, of course, as we're dealing with a sample size of 6. Using 100% to represent the underlying standard deviation, this means that we have a 24.1% chance that our actual measured standard deviation is between 90 and 110% of the underlying standard deviation. Okay, to try another example, how do we determine the chance that our measured standard deviation is in between 50 and 70% of the underlying standard deviation? Well, we can use the area from 0.5 to 0.7 for the low deviation case, or the area from 5 to 7 for the high standard deviation case. And again, you should see that both probabilities are identical. The high deviation case is 10 times wider and 10 times shorter, and both cases have the same basic shape. Doing this over and over, we can now form a table showing the probabilities that our measured standard deviation falls within certain percentile ranges of our underlying standard deviation. And this table is completely independent of what our underlying standard deviation is. Again, looked at this way, we get the same areas whether the underlying standard deviation is 1, 10, pi, or any positive number. So, we still have uncertainty in our uncertainty. In other words, uncertainty in our underlying standard deviation. But we now have a better handle on it. We now know the probabilities that our measured standard deviation is within certain percentage ranges of our underlying standard deviation. In fact, we can cheat and just use a plot where our underlying standard deviation is 100 watts and label it as our percentage plot. Think about it. For example, when we're looking at 50 watts here, we're also looking at the probability density at 50% of our underlying standard deviation of 100. So, we can go from one graph to the other, from powers to percentages. The only thing that changes is the labeling, like this. Here it is again. So, let's say that an all-knowing sage tells us that our measured standard deviation of 19.8 watts is somewhere in the 45 to 55% range of our standard deviation distribution. Or maybe we're just hearing things after all that beer testing. But either way, if that statement is true, what does it tell us about the underlying standard deviation? Would it be higher or lower than what we just measured? Please pause and ponder. Since the sage didn't tell us where our result falls within the 45 to 55% range, let's split the difference and assume that it's at the 50% point. Hopefully, you're seeing that our underlying standard deviation must equal the relative value of 100% by definition. Therefore, the underlying standard deviation will be larger than the measured standard deviation. In this case, our underlying standard deviation with a relative value of 100% would be 100 over 50 or twice as large. Hence, we would infer that our underlying standard deviation would be 2 times larger than our measured standard deviation of 19.8 watts. Like this. In that case, since we would know that the underlying standard deviation is 39.6 watts, we could simply draw a Gaussian PDF with a standard deviation of 39.6 watts about our measured average power of 55.3 watts, and we'd be done. Quite similar to what we did in the first video. Obviously, if the sage is correct, we have an absolutely huge standard deviation here. So huge that our PDF tells us that we have a very good chance that the underlying power consumption is negative. Obviously, that's impossible. Brighty bulbs can't consume negative energy. That would imply that some of their light bulbs could generate electricity, and they're definitely not claiming that. We always need to remind ourselves that mathematical models are just models, and that results should always be tempered with some common sense. They are only as good as our assumptions, and our assumptions are almost always just an approximation of reality. In this case, our assumption that the Gaussian distribution of Brighty bulbs merrily continues into negative powers is clearly a bad one. But if our assumptions were correct, and if the sage were being honest, then the appropriate PDF could be nicely approximated by a Gaussian curve, like this. Now, of course, we don't normally have a sage whispering things like this to us, especially when we're sober. Ultimately, we're forced to directly confront the uncertainty in our uncertainty. So what can we say? Let's return to the PDF of standard deviations. Here, we see that we have a 5% chance that our measured standard deviation is in that 45 to 55% range. Like before, let's approximate things by treating that entire range as if it's at the 50% level. In that case, we can say that there's a 5% chance that our measured standard deviation landed in this part of the distribution, and that the underlying standard deviation is therefore about twice as large as what we measured. Clearly, there are other possible ranges that our measured standard deviation could fall in as well. So, this one Gaussian PDF cannot be our entire answer. It's a PDF that's only applicable 5% of the time. In other words, when our standard deviation measurement just happens to unknowingly fall in that 45 to 55% range. So, how does this 5% chance in this PDF get reflected in our final PDF? Let's break it down a bit more by looking again at the Sage PDF. This PDF shows us that we have a 10% chance that our underlying average is between 50 and 60 watts. But because this isn't always the applicable PDF, we can't just say that we have a 10% chance that our underlying average power is in this range at the end of the day. What we can say is that we have a 5% times 10% or 0.5% chance that this is the appropriate PDF, and that we then have an underlying average between 50 and 60 watts. In other words, a 5% chance that our standard deviation is in that 45 to 55% range, so that this is the applicable PDF, multiplied by the 10% chance that our underlying power is between 50 and 60 watts, given that this is the applicable PDF. Think about this a bit. So, what should we do to this portion of the curve to account for this? Hopefully, you can see that we need to multiply it by 0.05 to account for the fact that we should only be using this curve 5% of the time. Like this. What do you think we'll have to do for a different region? say between 100 and 110 watts? Yep. It must also be reduced by the chance that this is the applicable PDF. So we multiply it by 5% as well. In fact, we should do this for the entire curve since there's nothing special about the power ranges that I've chosen here. So the entire curve should get multiplied by 0.05 as follows. Here it is again. Question: after doing this reduction, what is the total area of this reduced curve? Remember that it used to be 1. Now that everything has been multiplied by 0.05, its total area is now 0.05 instead. And this should make sense. Remember that we have an overall probability of 5% that this is the applicable PDF. Therefore, this PDF should have an area of 0.05. As such, it defines our final PDF for 5% of the overall probability space. This should be the contribution to our final PDF. A contribution that accounts for the 5% possibility that our measured standard deviation is between 45 and 55% of the underlying standard deviation. Can you predict what I'm going to do next? It's a really great sign if you can start completing my sentences for me. And don't worry, unlike my parents, I won't be offended if you do that. Okay, let's consider the 145 to 155% range of our standard deviations next. If our measured standard deviation is in this range, then we have overestimated the underlying standard deviation. We'll approximate everything in this range as if it's at the 150% standard deviation level. Our probability of being in this range happens to be 2.7%. So, if we're in this range, then the underlying standard deviation is 100% divided by 150%, or 2/3 the value of our measured standard deviation. In other words, 2/3 times our measured standard deviation of 19.8 watts. So, for this case, we'll use a Gaussian function that has the same average value of 55.3 watts, an area of 0.027, and a standard deviation of 13.2 watts. Like this. You should notice how this Gaussian has a much lower standard deviation. This causes it to get very close to 0 much more quickly. Also, perhaps a bit less obviously, since this is a less probable case, 2.7 versus 5%, it has only about half of the area of our previous Gaussian contribution. So, let's pull up our distribution of standard deviations again. Hopefully, you now see that we can approximate the final PDF by summing together the appropriately weighted Gaussian functions. One Gaussian function for each region of this PDF. In theory, we'd have to go up to an infinite standard deviation since the probabilities never exactly equal 0. But as a practical matter, we can see that the probabilities get so low after 200% that we can really stop there without giving up too much accuracy. Remember that this is an approximation only. We're just testing an idea. There's obviously some inaccuracy as well when we approximate everything and our 20% ranges is having the same standard deviation. So, let's go through these 10 areas more slowly and compute what we should be adding in for each of them. Our first rectangle on the left here is tiny and covers the 0 to 20% standard deviation range. So, we'll split the difference and treat all standard deviations in this rectangle as if they equal 10% of the underlying standard deviation. This means that if we happen to be in this region, our underlying standard deviation is 100% divided by 10%, or 10 times larger than our measured standard deviation. So that's a huge standard deviation. But keep in mind that this rectangle is tiny, so the corresponding Gaussian function only has an area of 0.001, or 0.1%. So, let's also look at the next rectangle. This one covers the 20 to 40% standard deviation range. We'll approximate everything in it as having 30% of the underlying standard deviation. This means that, for this case, the underlying standard deviation is 3 1/3 times larger than the standard deviation that we measured. the probability of our measured standard deviation being this low compared to the unknown underlying standard deviation is 2.2%, a bit larger this time. We'll now go through the remaining 8 regions more quickly. Watch how the title changes each time, and feel free to pause the video if you wish to examine them more closely. Here goes. As we move from left to right, our measured standard deviation becomes a higher percentage of the underlying standard deviation. Therefore, the computed underlying standard deviation becomes smaller and smaller as we move along from left to right. Now, we're ready to return to the 6 brighty bulbs that we actually measured. Remember that we measured a standard deviation of 19.8 watts. All we have to do now is replace what we just did using percentages with our actual measured standard deviation. So, for our example, 100% corresponds to 19.8 watts. Now, let's go through the areas again, this time with percentages being replaced by actual watts. Here's our first area again. Remember, the one that goes from 0 to 20% of the underlying distribution? Using the same 10% approximation as before, we compute the underlying standard deviation for this case as 100% divided by 10% multiplied by our measured standard deviation of 19.8 watts, or 198 watts. Again, we have the same very low 0.1% probability of being in this region as before. Here's the picture for our next area. Make sense? Hopefully, you're getting the hang of this by now. Let's quickly go through the rectangles again, using watts this time. Again, watch how the titles change. Here goes. So that's it. This is our recipe for approximating the student's t-distribution. We sum together Gaussians with various standard deviations, and each Gaussian is weighted by the probability that its standard deviation equals that elusive, unknown underlying standard deviation. And of course, each Gaussian function will be centered on our measured average power of 55.3 watts. In part 3, we'll see this in action as we create the student's t-distribution for ourselves.